Hello and welcome. In this video, we're going to be taking a look at a brand new coordinate system. Now, the coordinate system that we're familiar with x and y is called the Cartesian coordinate system. And we're so used to that trying to come up with any kind of new system for putting coordinates onto a graph is going to be a little bit tricky to kind of get used to. So let's see what we have already for our coordinate system and see how we can develop something that might be useful in certain circumstances instead of our classic x and y coordinates. Now, the Cartesian coordinate system that you see here is also the basis for the grid paper you see in the background. So we have an x-axis along the horizontal, and we have a y-axis on the vertical. Now, it's not necessary that these two axes need to be labeled x and y. In fact, a lot of times our horizontal axis might be t for time or something like that, but they form perpendicular axes. And where the two axes cross is called the origin. Any point on this Cartesian plane is going to be involving two values, one value for x and one value for y, and that comes in the form of an ordered pair. So let's suppose I have the point P at the coordinates 3, 2. That 3 is meant that we have to travel 3 units in the positive direction for x, and the 2 means that we have to travel 2 units in the positive direction for y. And that gives us our brand new point. Now see if you can think of another way so that we'd be able to locate a point. We don't need to travel simply right, left, up, or down. Instead, we're going to come up with this new system called polar coordinates. Now, with the polar coordinate system, surprisingly, we really only have one axis. This axis is going to measure a distance away from that origin. You can think of the polar axis here as really taking the place of our positive x-axis. It's safe to assume that this distance is positive. However, we can make sense of a negative distance as being a distance in the opposite direction. But a distance on its own is insufficient for coming up with a point anywhere on our two-dimensional plane. We'll need one more parameter, and that is a direction. Not just positive or negative, but a direction more like a compass bearing. Only instead of north being 0 degrees, we're going to measure our angle from the polar axis counterclockwise. With any angle, let's assume the angle may be between 0 and 2 pi, and a distance, which is positive, we should be able to arrive at any point on our two-dimensional plane. Now, instead of rectangular grid lines, though, this is going to cause us to have a very different looking system. Here's the result of introducing that polar axis and angles. You can see on our polar axis here, I have labeled distances 0, 1, 2, 3, and 4, and that would just continue onward. And we can see some of our common angles in radians, pi over 4, pi over 2, to pi, which is 180 degrees, all the way back around to 0, or 2 pi radians. The two parameters that we need in order to express any point is a distance, which we will use r, since it's kind of implied as like a radius, and that is the distance from the origin along the polar axis. And our second parameter is going to be theta, which is the angle measured from that polar axis counterclockwise. And so our coordinates are going to be r comma theta instead of x comma y. Let's see if we can plot a few points here. Let's start off with a point P located at 2 comma pi over 6. Well, for convenience here, I have got all of these minor grid lines increasing by pi over 12. Pi over 12, and then 2 pi over 12, which is pi over 6. You can see that pi over 4 is simply just 3 pi over 12. Okay, well now that we've got that direction of pi over 6, we need to travel 2 units outwards. 1, 2, and there is our point P. And so you can see that point P is in quadrant 1. But let's try point Q here. Q will be at the coordinates 3, 4 pi over 3. Now 4 pi over 3 is going to be a little bit beyond 3 pi over 3, which is pi. So let's start counting up by pi over 12 from there. Pi is 12 pi over 12, and then we have 13 pi over 12, 14 pi over 12, which is 7 pi over 6, 15 pi over 12, which is 5 pi over 4, and 16 pi over 12, which is 4 pi over 3. And there's our direction, and we need to travel 3 units outward. 1, 2, 3, and there's our point Q. All right, well now let's see if we can also use negative values for theta and for r. Let's look at the point capital R at the coordinates 4, negative 5 pi over 4. Whenever we see a negative theta, that means we're going to be traveling in our opposite direction, which is clockwise. So traveling clockwise 5 pi over 4, and we need to travel 4 units outward. 1, 2, 3, 4. And you'll notice that that point, capital R, can also be expressed as 4, 3 pi over 4. So unlike Cartesian coordinates, any given point may have more than one representation. In fact, there are infinitely many representations of each of these points, and we can get those by simply just adding a multiple of 2 pi to theta. What about if we have a negative r? Let's use point S here at the coordinates negative 2, 5 pi over 12. Now 5 pi over 12 is just a little bit shy of pi over 2. That's this second to last tick mark in quadrant 1. And 2 units outward should be going from the origin in a positive direction, but a negative direction will be opposite of that. So we're going to actually have to travel backwards along that same direction and go 2 units backwards from the origin. And so you can see that we can also express S as the coordinates 2, 17 pi over 12. And there again, we can see that there's more than one representation of that point. Now I should mention that it does get a little bit confusing if r is equal to 0. That would be the origin, in which case theta can be anything, and that would still be the origin. There's no direction for that one point. So they can get some peculiar behavior at the origin. Now I should mention that while there are infinitely many ways to represent a point, all points other than the origin can be represented with a positive r and a theta from 0 to 2 pi, including 0, but not having to include 2 pi since it would give the same direction as theta equals 0. Now it may really help to know how to convert between these two different coordinate systems. They should both cover all of our two-dimensional plane, so there should be a way to convert from one to the other. And I find it's very helpful to draw a little diagram so that you can remember a couple of these conversion formulas. Here you can see that I've overlaid the two different coordinate systems. We have our x and y coordinates for the point P, and we have our r and theta coordinates for the point P. And if they are equivalent, then they should obey some laws given by this right angle triangle. If we wish to represent this as a triangle with r as our hypotenuse, x is equal to r cosine theta and y is equal to r sine theta. This is going to be a very good way of converting from Cartesian coordinates to polar coordinates because we can make these two substitutions. Any function that has x's and y's in it, if by making these two substitutions, we can come up with a relationship involving r and theta. It's not quite as easy the other direction around. If we have a relationship involving r and theta, then we can still use some trigonometric properties and our classic Pythagorean identity. We can see that r is equal to the square root of x squared plus y squared, and that will give us a positive r. And theta, well, we would have to use some kind of inverse trigonometric function here. We'd have to use arctangent. But the problem with that, with arctangent, is that it's only going to give us an angle from negative pi over 2 to positive pi over 2. So I wouldn't recommend using these two relationships. Oftentimes, it's actually better to just use x squared plus y squared equals r squared, and y over x equals tangent theta. Using these two relationships, you can see that we can either end up with a positive or a negative r, depending on what makes the most sense, and theta will have infinitely many different possibilities given a y and an x. We'll have to determine whether theta is in quadrant 1, 2, 3, or 4. Let's try a couple examples. Let's take the coordinates 4, 7 pi over 6 in polar coordinates and convert that to Cartesian coordinates x and y. And let's also take a look at 2 root 3, negative 2 in Cartesian coordinates and convert those to polar. The good news is we won't actually need to necessarily graph these. We just need to know which quadrant we're talking about. Given that polar coordinates are always in the form r comma theta, that means that to find x, our r is 4 and our theta is 7 pi over 6. 4 cosine 7 pi over 6 gives us negative 2 root 3. Similarly with y, we just need to look at 4 sine 7 pi over 6, and that gives us negative 2. Hopefully that makes sense because we have a positive radius and 7 pi over 6 is going to be in quadrant 3 where x and y should both be negative. We can write that as an ordered pair. Now, converting the other direction around, given an x and a y, we should already know what quadrant we're in. Since x is positive 2 root 3 and y is negative 2, this means that we need to be in quadrant 4. And it's best to try to express every point with a positive r and a theta from 0 to 2 pi. Using our Pythagorean identity, 2 root 3 squared plus negative 2 squared, that is 12 plus 4, and that gives 16 equals r squared, and taking the positive root, r will equal 4. Of course, there would be another solution where r equals negative 4, but it's generally better to have a positive distance r. Now, to find theta, 2 root 3 divided by negative 2 is equal to the tangent of theta, and we could simplify that to negative root 3. And solving the equation negative root 3 equals tangent theta has infinitely many solutions, but we're going to be looking for one specifically from 0 to 2 pi. We can use a little reference triangle here to help us out. In quadrant 4, we will have a vertical component of negative root 3 and a horizontal component of 1. That reference angle is pi over 3. So, to find our angle theta, oriented from the polar axis in a positive direction, we just need to take 2 pi minus pi over 3. Since 2 pi is 6 pi over 3, subtracting pi over 3, this is 5 pi over 3. So our ordered pair, r theta, with the restriction that r is positive and theta is between 0 and 2 pi, would be the coordinates 4, 5 pi over 3. Now that we've got the basics of finding and plotting a point on a Cartesian or polar coordinate axes, let's see if we can turn this into a graph of a function now. When we start thinking about graphing in polar coordinates, then there's a couple of different options for what kind of relationship we might be trying to graph. Just like with Cartesian coordinates, we might be looking at some kind of function. Only instead of y being a function of x, we might be thinking more as r being a function of theta. However, just like with Cartesian coordinates, not all curves are functions, and so we may have some kind of implicit relationship between r and theta that would be given in the form of an equation. In either case, the graph consists of all points r comma theta that satisfies that relationship. Now, when we're graphing in polar coordinates, we can get some really interesting graphs immediately. A lot of times it's kind of a useful system for things that have rotational symmetry, such as just graphing a circle. That would be a pretty straightforward thing to look at, and one of the examples we'll do here in a moment. But also, we get some really interesting behaviors because, for instance, what if our domain for theta was, instead of from 0 to 2 pi, it could be all real numbers, in which case we could still have a function of the form r equals f of theta, and we would end up going around our origin infinitely many times, but still being a function. So you can come up with some really interesting spirals and all kinds of interesting patterns out of this. Now, for convenience here, I've just included our polar axis, and again, from r equals 0 to r equals 5. Let's start off with a graph of r equals 3. Now, if it just is given as r equals 3 and you don't see theta in here, or even if you were to have r equal a function of theta, it would probably make a lot of sense to know what the domain is. Since it may not be all real numbers, let's say in this case we just want theta from 0 to 2 pi, which is pretty common. Well, in that case, the graph consists of all points where the distance from the origin is equal to 3 units. And theta goes once of the way around our entire circle. So this actually creates the graph of a circle of radius 3 centered at the origin. And there is that graph. Now, when theta equals 0, that is the coordinate 3, 0. And when theta is equal to 2 pi, that's also the coordinate 3, 0. So this function actually includes that point twice, once at each end of that interval. All right, well, that's a function since it can be expressed in the form of r equals a function of theta, even though it is just r equal to a constant. Let's take a look at theta equals a constant. Now, this isn't a polar function in its standard form where r equals a function of theta. Think about this as kind of like when we want to graph a vertical line, we would just say that x equals 3 in Cartesian coordinates, and it's implied that y can be any real number. Well, in this case, theta is equal to a constant, and r is any real number. Okay, well, pi over 6 is going to be in quadrant 1. It is right here, just a little bit shy of pi over 4. Now, r is any real number, so that would mean that r could equal 0, r could equal 1, r could equal 2, or any positive value. But since we're also allowing real numbers, that's going to involve all the negative values. And so what you get whenever theta is equal to a constant is you end up with a line passing through the origin. And of course, that line is also at 30 degrees here on my ruler. Now, a small little modification here, if we were to say that r was only greater than or equal to 0, well, then we'd have to change the graph slightly. This would eliminate all of those negative values of r, and instead of a line passing through the origin, we would end up with a ray. So be a little bit careful about what kind of values we can actually allow. If we have r equal to a constant or theta equal to a constant, then the domain of the other parameter is quite important. All right, well, now that we've taken a look at r constant and theta constant, let's look at a little bit more interesting function. Let's suppose that r is the function theta, and theta is greater than or equal to 0. Well, we could use a table of values, and we could even just kind of do that mentally here. If theta equals 0, and we plug that in, then r equals 0. And that would give us the origin. Okay, well, when theta is equal to pi over 4, then our distance has gone to pi over 4. All right, pi over 4 is, close to 0.8, a little bit shy of 1. When we have theta equal to pi over 2, then r is equal to pi over 2, which is about 1.57. And you can see that as we increase angle, we're always increasing distance away from the origin. So when we get to, let's say, theta equals pi, then our distance from the origin is 3.14 units. Now, can you try to imagine what this graph looks like? As we go around in this counterclockwise direction, we're getting farther away. It's a linear relationship, though. This would result in a spiral. We will travel farther and farther away from the origin as theta increases. Now remember that a spiral would be pretty difficult maybe to try to implement in terms of Cartesian coordinates, but you think about how simple this is in polar coordinates. When we switch coordinate systems, you have to really think that simple shapes in one don't necessarily mean simple shapes in the other. All right, last but not least, since we are involving angles, you can imagine that a lot of these functions will probably involve trigonometric functions. So let's take a look at the example r equals 4 cosine theta, and let's say that theta is just in the domain from 0 to 2 pi. Now with this one, we are almost certainly going to want to actually write down a table of values. Since r is a function of theta, we'll choose values for theta and determine the value of r. And of course, let's start off with theta equal to 0. When theta equals 0, r is going to equal 4. Try to use some of your very common angles at this point in time, maybe such as pi over 6. When theta is equal to pi over 6, we end up with 4 times root 3 over 2, which is 2 root 3. When theta is equal to pi over 4, this is 4 times root 2 over 2, which is 2 root 2. When theta is equal to pi over 3, this is 4 times a half, which is 2. Getting to the end of that first quadrant, pi over 2, this gives us the value 0. So we can start plotting that first quadrant right away. In that first quadrant, from 4 to 2 root 3 to 2 root 2 to 2 to 0. What happens when we reach quadrant 2? Well, you have to think about what happens with the graph of cosine theta as we've gone from our starting value of 1 to 0 at this point in time. Remember that cosine of pi is negative 1. And we will end up with the exact same values here, but simply just being negated. So if we wish to continue, then we'll see that we end up with the same values in the negatives. -2, -2 root 2, -2 root 3, and -4. Remember that with negative radiuses, this is just like 180 degrees or pi radians rotated around from the given theta. So in the direction of 2 pi over 3, but 2 units in the negative, that puts us back here somewhere. And you can see that that actually is a nice mirror image of one of our points over the positive x-axis or our polar axis. And 3 pi over 4, but 2 root 2 units in the negative direction. 5 pi over 6, but 2 root 3 units in the negative direction. And finally, theta equal pi, but 4 units in the negative direction puts us right back at our initial point. And if you take a look carefully, what we've actually graphed here is a circle of radius 2 centered 2 units to the right of the origin. We haven't actually gone all the way from 0 to 2 pi though. What's going to happen if we continue this table of values? Well, because a lot of the symmetry of cosine theta here makes these calculations easier, you can see, of course, well, 7 pi over 6 is going to give us -2 root 3, which is actually the same as the point that we had at pi over 6, +2 root 3. At 5 pi over 4, r evaluates at -2 root 2. That's the same point as pi over 4, +2 root 2. And you see that what we end up doing is we've actually gone around this green circle here twice. So this graph produces a circle of radius 2 centered at the point 2 units to the right of the origin, but it also graphs that circle twice. All right, well, now that you've seen a few examples, some of them are a little bit trickier than others to try to plot by hand. And if you're really stuck, it is always helpful to know how to plot in polar coordinates on a computer. So let me show you in Maple how you can achieve this sort of result. It's fairly straightforward. It's just using the typical plot command, but with a few extras. So we've got this plot command here, and there's that function for cosine theta. And let's suppose I want to plot from theta equals 0 to 2 pi. Now right away, if I do that, it's going to assume that we want to have theta on the horizontal axis. And you can see, of course, this is in fact just a graph in Cartesian coordinates. We're pretty familiar with this, but we need to change that system. We're going to change these coordinates to polar. Coords equals polar. And sure enough, that switches the system immediately and gives us a circle of radius 2 centered at, well, in Cartesian coordinates, the point 2, 0. And sure enough, we can see what happens if we only have 0 to pi. Once again, we end up with the same shape. So really, we don't need to actually involve theta all the way from 0 to 2 pi. Now let's try a couple other interesting looking graphs in polar coordinates. If I were to change cosine to sine, you see that we still have a circle of radius 2, but this time it is centered at a point 2 units above the origin. Now suppose I wish to shift that. If I were to add a value onto this, such as +1, this isn't just a shift up or right. This is a shift of 1 unit in r, which is going to be a little bit bizarre here. In this case, let me go back and plot from 0 to 2 pi. And you can see we have a very interesting looking shape. And that's because in certain occasions where r is negative, we're adding 1 to that, and we may still end up with a positive radius. And in other occasions where 4 sine theta ends up being negative and adding 1, we end up with a possible negative value. So this is still going around from 0 to 2 pi, and occasionally the radius is positive, occasionally the radius is negative, but it isn't the kind of shift that you might expect. It would probably be most useful, once again, to just make a table of values and be able to figure out whether or not that radius is positive or negative. If we wish to always have the radius be positive, let's suppose we just want to change sine to sine squared. Well, that makes a pretty interesting looking shape. Sine squared is always going to be positive. And so as we travel from theta equals 0, we end up with 1. And as we travel all the way up to pi over 2, then we end up with 5. We end up traveling to r equals 1 when we're back to 3 pi over 2. back to 5 when theta is equal to 3 pi over 2, and back to 1 when we reach the end of the circle. Let's get rid of that 1, and you can do all kinds of interesting things with this. Let's suppose that we wanted to change the period of theta. We'll make it extra fast, and let's say we want to have 8. Well, you can see that the oscillations are much quicker. Still, we have the radius always being positive, but going from 4 to 0, and you can see that there are 16 of these little spikes all the way from 0 to 2 pi. So you can make some really interesting graphs, and particularly as you see here, it's very quick to make graphs with rotational symmetry. Now, unfortunately, there are some downsides. There are going to be functions that are very easy in Cartesian coordinates to graph, but when you change those into polar coordinates, they aren't quite as nice. For instance, if we just wanted some sort of straight line that does not pass through the origin, then that's unfortunately going to be a lot more difficult to use polar coordinates for than to just use y equals mx plus b. Similarly, if you have a circle, it's much easier to express that if it's centered at the origin in polar coordinates than when it's centered at some random point x, y in Cartesian coordinates. So there are strengths to each of these systems, and it really comes down to a little bit of practice as to when you know one system is better to use than the next. So hopefully that gives you a little bit of an overview of polar coordinates. You get an idea of at least how to plot points and what some very common shapes would look like, particularly circles and lines through the origin, and some of these sort of interesting spirals that you can get. We'll look at this in the future and see how this is going to help us to do a little bit of calculus on those types of curves later on. Thanks for watching, and I'll see you in the next video.